So in this lesson, we're going to go over intermolecular forces. Now, most of this, 95% of this should all be reviewed from grade 11, but let's take a moment now and go through it. So intermolecular forces. Okay, so remember that an intermolecular force and an intramolecular force are very different. So an intermolecular force is an interaction, not a bond, but an interaction between two molecules. They could be the same ones or different ones, but they're an interaction between two separate molecules. A covalent bond is an example of an intramolecular force. Now, this is an actual bond within a molecule between two atoms. Now, having said that, making sure you're paying attention, here's a question. So, is a covalent bond an intermolecular force or an intramolecular force, and why? So, take a moment, think about this, pause it before I reveal the answer. Go ahead, press pause. Great, now that you have thought about it and unpaused, here is your answer. So, because it forms an interaction, a bond between atoms, it's an intramolecular force, right? Covalent between atoms in a molecule, intra. Okay, now intermolecular forces are significantly weaker than covalent bonds, much weaker. However, it's the number of them that really contributes to changing properties of substances. So a little bit of history here. Johann van der Waal was one of the pioneering research scientists that studied intermolecular forces. So we have then our van der Waal forces, or our weak intermolecular forces, that we will talk about now. There are three kinds. Let's make a new slide here. Okay, so we're going to begin with the weak intermolecular forces. Of these, there are three. So first, as you just saw, is your dipole intermolecular force, weak intermolecular force, right? Then there is hydrogen bonding. Which is strange that it's called bonding because it's not actually a bond. It still is an intermolecular force, but it's called hydrogen bonding. Third one, the weakest one, is your London dispersion forces. Okay, so those are your three weak intermolecular forces, or your van der Waal forces. Now, these next two are your strong intermolecular forces. So here we're going to talk about ionic interactions, or ionic-ionic interactions. Well, that looks messy. Or forces. Makes things like crystals. Your second strong intermolecular force is your dipole. Ionic force, or dipole ionic. Messy again. Let's correct that. Okay, so 5 forces, 3 of which we're going to focus on the most, and these are your weak intermolecular forces. Okay, so a dipole-dipole intermolecular force occurs between oppositely charged dipoles. So if a molecule is polar, so has a positive and a negative end, the interaction between the oppositely charged ends, a negative and a positive, is your dipole-dipole interaction. Right, here are some examples. Here we have, it helps to draw this out. So let's say this dichloroethane here. Won't exactly name it because we've already done that in our organic chem unit. This is a polar molecule, so we're viewing molecular polarity from grade 11 briefly. This end has a greater electronegativity because of your chloride atoms here, so we're going to have a negative dipole here, and if electrons are being pulled in this direction because of this greater intermolecular force, that means this portion here is going to have a positive dipole. So this polar molecule can then interact with other poles of other molecules, creating dipole-dipole interactions. Right? And these red arrows here show the direction of this increased pull because of differences in electronegativity. So bromine here creates a negative dipole here and a positive one here. So what will happen is your negative and positive, so this negative here, positive here, are going to orient themselves. So here is your chlorine here. Let's see, negative bromine. Chlorine's going to be in a positive direction here. Oh, chlorine's negative here, which means this end over here is going to be positive. Now you can see that positive and negatives interact, positive, negative interact, positives and negative interact. So these are interactions between oppositely charged dipoles in polar molecules. That's your dipole-dipole interaction, right? So the strength of a dipole-dipole interaction is directly related to the polarity of the molecule. So if you're ever asked to compare the dipole-dipole interactions between two different sets of molecules, you're looking at the difference in electronegativities. Now, you will have more questions on this. Feel free to ask to clarify. Right, so the more electronegative one substance is, the more polar you could say it is, and therefore the greater intermolecular forces, dipole intermolecular force it's going to have compared to something else. Okay. Already mentioned that it occurs between only polar molecules. Right, individually, the force, like we mentioned, is almost insignificant, but a container, a flask, a beaker of this really does change things, physical properties, like melting boiling point, um, things like that. So next kind is hydrogen bonding. Now, very similar to dipole-dipole interactions, except because of its ubiquity and its um, necessity for human life, for life, not just human life, but for all life on Earth, and its stronger interactions, it has its own category. So hydrogen bonding occurs whenever you have hydrogen bound to oxygen, nitrogen, or fluorine. Okay, you can make up a word. I know students usually do. NOFs, whenever you have hydrogen with NOF or nitrogen, oxygen, or fluorine, you know it's going to be not dipole-dipole interactions, but hydrogen bonding. So same idea here, you have an interaction between a negative dipole and a positive dipole, so opposite partial charge or opposite charges will align themselves to interact. Now this is normally what happens, of course, with dipole-dipole interactions, but because this is happening between oxygen in this case and hydrogen in a molecule that has, right, water, great example, oxygen and hydrogen, or it would be oxygen, nitrogen, or, sorry, let me say that again, hydrogen and oxygen in this molecule in water. But the same thing would happen with a molecule that has hydrogen and nitrogen, or hydrogen and fluorine. Okay, so that's hydrogen bonding. Right? In a 2D depiction here, we have these dipoles aligning so that we get attraction between a positive and a negative, right? Positive and negative, all three out. Now imagine this just between 4 water molecules in 2D. An entire beaker full of water molecules will have much greater interactions that we can possibly draw here. Here's some more in more of a 3D depiction here, just to show you a sample. Okay, so hydrogen bonding can explain then why water, well, not just hydrogen bonding, but it does help explain why water expands as it freezes. Okay, I will leave that question for you to ponder and we can talk about together. So why does water expand when it's frozen? Part of the answer is here. Okay, so as kinetic molecular energy is lost through cooling, water begins to move slower, allowing then for the creation of more of these hydrogen bonds. So more hydrogen bonding means more intermolecular forces, more distance that causes expansion. So as they begin to slowly move around, crystals of ice begin to form inside of this pipe. So increased hydrogen bonding will cause repulsive forces. Now, this is the part that isn't directly related to intermolecular forces, but it causes, let's just draw a couple of water molecules here. A bond and an intermolecular force, or a bond distance. Now, they will attract until they begin to repel, right? Because they do actually repel. There are, after all, electrons floating around oxygen here, so they will, and not to mention their protons will certainly repel each other. But there will be a distance created between these two dipoles. So as these crystals slowly begin to form, they will increase their volume because they have more hydrogen bonding, which causes an increase in distance between those molecules, and therefore your pipes burst. Okay, we got sidetracked there for just a bit, but I think that's a great example to talk about. Last van der Waals force, last weak force is your London force, okay, or your dispersion force. So this happens for everything really, but we're going to focus on nonpolar molecules. Right? If I haven't drawn an example of this, I think I'll do that now. Right? So let's look at butane. Okay, butane has 4 carbon atoms. We'll fill in these hydrogen atoms quickly. Okay, this is and as I do, I'll talk about butane. We know that butane this is just a Lewis structure stick diagram of it, but we know that it is a very symmetrical molecule. It is a very non-polar molecule, so there are no dipoles, right? So you would think that there are no intermolecular forces. Dipole-dipole forces aren't happening, and certainly hydrogen bonding isn't happening, but these bonds aren't static. We know that there are brief instances, not a second, not half a second, but just an instant in time where this hydrogen here might move here. Now, this doesn't tend to happen, right? It wants to maintain that tetrahedral shape around the central carbon, but just for an instant, will not happen for long at all. But just for an instant, what happens here is you make this molecule not symmetrical. So we expose a carbon here briefly to create a momentary dipole. In another butane molecule, this can induce a dipole. So what this can cause, and I won't draw the rest of the hydrogens here, but this can cause another dipole. But the rest of the hydrogen, I will draw them because I feel badly not drawing them. It's wrong if I don't. Okay, so between this instantaneous or momentary dipole, we're going to get, what did I draw here? This is actually supposed to be positive, right? So negative dipole here, positive dipole on this end. We get an interaction, London dispersion force, that doesn't exist for long at all. That's why it's your weakest intermolecular force. Like I said, this doesn't just happen for molecules; it happens with everything. We look at neon. Neon and all of its electrons are generally randomly moving. You know, we can talk about the quantum space and probability of electrons existing in this cloud of electrons, but they can be, for just an instant, especially if they're really cooled, they can slow down to create an uneven dispersion of electrons, so that one end could have a positive dipole and another end can have a negative dipole, and that can create a London dispersion force that will cause an interaction between two of these neons, these noble gases. This one noble gas. Okay, so again, electrons are always moving, but they can create instances where partial dipoles can exist, especially if they are cooled. And this can cause a very weak instantaneous dipole. Right, this happens, like I mentioned, for low temperatures. It's much easier for these dipole moments to last longer and therefore create these interactions, or for larger atoms. Kind of like playing the lottery here, or buying raffle tickets. We saw what can happen with butane, right? Butane, if you've ever seen a butane lighter, it's kind of at the phase between liquid and gas. But if we look at octane, let's not draw all the carbons. If we look at octane, 1, 2, 3, 4, 5, 6, 7, 8. Let's say octane is normally one of the things inside gasoline. We know gasoline to be a liquid. Now the reason it is, part of the reason that it is a liquid, if we consider just octane, although that's not entirely the whole picture, but if we look at just octane, it is a larger molecule than butane is. It's double the size with 8 carbon atoms, 8 possible places where dipoles can exist, even if for just a moment. Increasing, therefore, so increasing intermolecular forces, and that allows us to see that it allows octane to exist in a liquid phase as opposed to a barely liquid at slight pressures inside a butane lighter, or even methane, a natural gas which doesn't at room temperature exist as a liquid, right? Not a huge probability here for a London dispersion force to happen, although it can if we lower the temperature compared to butane or octane. Right, talked about temperature and how that can influence London dispersion forces. And the ability for a substance to form these momentary dipoles. Now that is referred to as its polarizability. Right, and again, it's dependent on, as we saw, the size of the molecule, the number of atoms it has, and temperature. Right. So in practice work that you'll have, it'll ask you if a substance, what intermolecular force a substance can have, and you have options between dipole, hydrogen bonding, or London dispersion. You'll always get part marks if you write London dispersion. That is always present. Now, if the question asks you what are the predominant forces, well, then that's a bit different. You can't necessarily put this, although if that is the only force, then you'll only run it once you write that down. Refer to your homework, ask questions, we'll go over examples. But typically, you can have water, for example, like we talked about, will have hydrogen bonding, but it will also have London dispersion. Okay, so those are the three. We're half done here, over half done. Those are the 3 weak intermolecular forces. Now for the strong ones, is the strong ionic attraction or ionic interaction. I've heard it called a few different things. These are just the interactions between ions in a crystal. So we look at, let's see, sodium chloride here, so regular table salt. Now they will form something called a crystal lattice structure. That's just a 3D arrangement of these ions causing intricate crystal lattice shapes depending on the different ions. Interactions between a positive sodium ion and a negative chloride ion, not just in 2D as we've usually seen between one chloride and one sodium atom, but as a crystal between many. Right? Very strong interactions. Imagine 2 tiny magnets, atomic sized magnets holding onto each other. That's why you can't melt salt on your kitchen stove. Dipole ionic forces are, as the name suggests, interactions between a dipole, such as those that exist in these water molecules here, and an ion such as chloride or sodium. And it helps to explain the dissociation of salts in water, of ions in water. So sodium chloride, although quite strongly held inside a crystal lattice structure, and we'll talk about the energetics involvements in our next unit, can dissolve in water. And the reason it can do that is because these ions can interact with the dipoles of water. Hence name again, dipole ionic forces. The negative chloride ion will have water molecules surrounding it in this way, where you have your positive hydrogen atoms, your positive dipoles interacting with a negative chloride, whereas your positive sodium ion will have the negative dipoles of oxygen surrounding it, and hydrolyzing it, and surrounding these 2 ions, just in slightly different orientations so that they match, or that they match their dipoles in the sense that one is positive and here this is negative, or negative and here sodium is positive. Right, that is it. This is a great worksheet to practice. Let me know if there are any questions. What you will want to define for yourself using reading in your textbook are these capillary action and cohesion and adhesive forces. We will talk about this more when we meet.